With so many agentic frameworks to choose from these days, OpenAI has released its open source agent framework called Agents SDK or OpenAI Agents, aiming to compete with LangChain, Microsoft AutoGen, TrueAI, and Pydantic AI. Given the OpenAI Agents framework had a late start, the framework has largely adopted the design patterns from existing agent-based architecture from other competitors to ensure it covers all the functionalities, standards, and autonomous infrastructure. In this OpenAI Agent SDK crash course, I'm going to walk you through everything you need to know to get started with the OpenAI Agents SDK in Python. This is going to be a beginner-friendly course. The only thing you need is some experience using Python and have an OpenAI account. Right now, I am starting to see OpenAI partnering with other companies like Box and Coinbase to integrate the Agents SDK with their service. If your company uses OpenAI or you use OpenAI models exclusively, then the OpenAI Agents SDK is a great choice for building autonomous agents and agent workflows. If you haven't created an OpenAI API key, please do so in your OpenAI project and save the API key as an environment variable called OpenAI API key. In terms of the agenda, these will be the 7 topics I will be covering in the course. I think that pretty much covers everything you need to know. If I miss anything, please let me know in the comments below. To get started, launch your terminal and run the command to install OpenAI agents, DuckDuckGo, and rich Python libraries. If you never used Rich before, Rich is a lightweight Python package for writing rich text to make the console output look pretty. And I would also highly recommend you use a Python virtual environment to isolate the dependencies. And we will use DuckDuckGo to create a web search tool to give our agents web search capability. To get started with using the Agents SDK, in your code editor, create a Python file and code it agentrun.py. In the script, import the Python dependencies shown on the screen. The agent and runner classes are all you need to create and run an agent. If you're not familiar with what an agent is just an AI model configured with instructions, tools, and whatnot. The async OpenAI class here is used to configure OpenAI API connection access. To set up the model access, create an OpenAI responses model object, and we will call it AOLM model. To create an agent, use the agent class and configure the settings. Name is the identifier for the agent. Output type is basically the same thing as a structured output, which defines the output data type. Instructions is the system prompt to define agent's role and behavior. Now, one thing the Agents SDK is doing differently from other frameworks is how you run an agent. With most of the agentic frameworks, agents have their own run method. But in the OpenAI Agents framework, we have this runner class to run agents. I believe the purpose OpenAI is implementing the agent run this way is to make the workflow more flexible by being able to swap the model in each run. And you can update the setting and hooks more easily this way. There are 3 options to run an agent. The most basic method is using the runSync function to run an agent synchronously, meaning the agent must wait for a task to complete before moving to the next task. In the runSync method, we need to provide the starting agent to run the request and the input to pass users' requests. There are other optional parameters like context, max turns, hooks, and run config to manage an agent run, which I will cover in a different example. Now, if I run the script, if everything is set up correctly, you should see the token usage output from raw response and the agent output. Now, pretending that I give an agent a request to perform 3 different tasks: send an email, update a Google Sheet, and check my calendar. Because the 3 tasks are completely independent, instead of running the task synchronously one by one, we can use the run method to do an agent run asynchronously to perform multiple tasks simultaneously. The drawback with running an agent asynchronously is it is a bit difficult to troubleshoot. And if you want an agent to stream the output, use the runStream method to print the output. When you use the runStream method to do an agent run, it will first return a run result streaming object. You can think it as a generator containing the streaming events. To print the output, iterate the stream events method to stream the data deltas. Now that we know how to run an agent, let's learn how to create tools. When working with agents, tools are anything an agent can use to perform a specific task like making an API call, send an email, create a file, etc. A tool can be a Python function or an API. 90% of the time when we talk about agent tools or toolkits, we are referring to functions. Now let's look at an example on how to create a function tool for an agent to use. To create an agent tool function, from the agents module, import the function tool function. OpenAI also offers their own built-in tools for web search and file search. But using their hosted tools comes with a hefty price tag, which I will share the pricing detail later. Personally, I would recommend you create your own toolsets to replace OpenAI hosted tools. And for this lesson, we will create our own web search tool function based on DuckDuckGo search engine, which is completely open source and free. Here, create the DuckDuckGo search function with the parameters to configure the search query. A few important things to know when creating an agent function. First, you cannot have optional parameters or set a default value in a parameter. Second, type hint and docstring will greatly improve the accuracy how agent will use tool functions. And to convert a function into an agent tool, wrap the function with the function tool decorator, and that's it. Some of the agent frameworks requires function output to be a string, but in the Agents SDK, we can return the output as a data class directly. To give the function tool to an agent, when you set up an agent in the tools parameter, insert the functions the agent can use. And here's the pricing when using OpenAI's hosted tools. For the web search tool call, depending on the model and context size, it can be as low as $25 or $50 for 1,000 calls. File search tool call will be an extra $2.50 for 1,000 calls for the responses API. Honestly, if you know how to use Python, you can create those functions yourself to avoid the expensive price tag or find alternatives. And the rest of the code is the same. If we change the output type to string, the agent will return the response as a natural language like ChatGPT. Now, when an agent makes a tool call, it is treated as a separate request call. If we iterate the records from response.raw responses, here we can see that the agent made two function tool calls, one as a new search type and one as a web search type. It then combines the outputs from the function calls, organize it as the final output to deliver to the end user. In some use cases, you might want to use agents as function tools. For example, you might have an agent that is specialized in data processing and is not part of a multi-agent workflow. If we look at the example here, I have two agents. Each agent serves as the gatekeeper that is responsible to retrieve API key. And to use agents as tools, in the tools parameter, insert the agent and use the as tool method to convert an agent into a function tool. Tool name and tool description are required fields when you convert an agent into a function tool. If we run the script, from the raw responses, we can see that do responses are generated to create the final output. First, the AWS API key agent tool is called with the input as the argument. From function tool called response, the agent then formats the information into the final output. That's all for this lesson. For the next lesson, we will learn how to make an agent to make multiple tool calls simultaneously. One of the coolest things when incorporate AI agents into your workflow is they can run tool calls asynchronously, meaning the agents can run multiple function calls simultaneously without waiting for one task to finish before starting another, which greatly boosts efficiency and saves a ton of time. To enable functions to be executed asynchronously, when you create a function tool, add the async keyword in front of the functions to convert them into asynchronous functions. In this example here, let's assume that function A and function B are two entirely independent processes with no connection between them. The sleep function is going to simulate the duration those processes is going to take to complete. And when you do an agent run, use the run method to initiate the request and wrap the agent run code in an async function. Pretty straightforward. If I run the script, from the log, we can see that function A and function B are called almost the same time. And here, function B finishes, followed by function A. Very powerful stuff if you use it correctly. Now let's dive into the next lesson, create a conversation and configure the agent run. So far, we've covered how to set up and run an agent call. However, 90% of the use cases will involve a conversation. In this lesson, we are going to learn how to create an agent conversation, configure an agent run, and context implementation. Here, let's set up our agent first. To create a conversation session, first, we need to create an empty list to store user and agent messages. And to keep a conversation going, create an infinite while loop that continues until the user type exit or quit to terminate the session. Inside the loop, we need to append the first message from the user to the conversation list to start, then use the conversation list as the input. When the agent returns a response, we need to call the toInput list to return the message history and updates the conversation list. And this is basically the implementation to create an agent conversation session. And here, let's run the script to test it out. Now, this is just a very basic use case. In the real world, you will probably deal with swapping models, control model settings, set max tokens, and provide relevant information as context. To implement a context, we need to have two things: a data model object to store the information, and a tool function to retrieve the information. Here, let's say I want to provide the user's information to the agent to make an agent interaction more personalized. I will create a user info data model to store the user's name, location, and occupation. Then create a tool function with a run context wrapper as the parameter for the agent to retrieve the user's info. Now create a user info object with the user's info. If we look at the run sync parameters, some of the things we can configure, such as max turns, hooks, run configuration, and context. In the run sync method, let's set the max turns to 3. The term max turns is a little bit confusing here. It refers to the number of iterations the agent can perform in its loop before stopping. For example, If an agent needs to make multiple tool calls to generate a response, and each tool call is counted as a single turn, then after 3 tools calls, a max turns exceed exception will trigger. And in the context parameter, add the context object we just created that contains the user's info. If you use ChatGPT or Gemini, you know we can change the model anytime when we send a message in a message chain. To do that, in the Agents SDK, in the runConfig parameter, use the runConfig class to specify the new model settings. And here I forgot to add the getUserInfo function to the agent tools. If I ask the agent about my information again, it should be able to answer them correctly this time. That covers everything we need to know about running an agent conversation. Let's learn how to switch agent in a conversation with Agent Handoff. In this lesson, we are going to learn how to implement Agent Handoff. Agent Handoff is the process of transferring a task from one agent to another. This allows specialized agents to handle different parts of a conversation or workflow, greatly improve overall efficiency and modularity. Let's look at an example how to implement Agent Handoff. In the script, import the Python dependencies and set up the LLM model. For the example, I will create 3 agents to simulate a retail workflow where one agent is responsible dealing with customer-related issue, one agent dealing with refunds, and one agent dealing with balance due. And I will create 2 function tools to simulate payment refund and check balance due. Here, we will create the refund and balance due agents first with the 2 functions assigned. Then create the main agent as the starting agent in an agent run. One of the most useful features using the Agents SDK is there are different triggers available. With the Agent Handoff, we can create a trigger method called onHandoffTrigger that fires whenever an agent is transferring to another agent. You can use the onHandoffTrigger to log additional information, provide more context to the transferred agent, or apply additional business rules. These are just a few use cases. When you create an onHandoffTrigger function, you must include the parameter to pass the handoff inputs. In this case, we will include a parameter for the refund reason. In the main agent setup, which is the customer agent, in the handoffs parameter, use the handoff function to specify the target agent. Handoff function will be invoked and input data type. When we create the refund and balance due agents, because the main agent isn't created at that point, and we want to be able to include the customer agent as one of the handoff agents. To add an agent to the agent handoff list dynamically, we can use the handoffs append method. At this point, we have a team of agents ready to tackle different tasks. You can think of it as a department with different divisions. Each division is responsible for dealing with different type of issues. Create the while loop to implement the agent conversation session. With the agent handoff, when an agent transfers to another agent, we need to ensure that the active agent remains the one from the previous turn. To achieve this, create an agent tracker to keep track of the active agent and use the agent tracker as the starting agent in each turn. That's basically how I would set up the agent handoff implementation. Now let's run the script to test the handoff. For the initial request, I will ask, I need to return my book for a refund. Now the customer agent identifies this is a refund request. It needs to transfer the task to the refund agent. Remember, when we set up the main agent, we use the handoff function to include the onHandoffTrigger and input type, which is the refund reason data object that contains a field called refund reason. So here, the main agent needs us to provide the refund reason first as the required context to be able to transfer to the refund agent. For the refund reason, I will say, I already bought the book. The onHandoff trigger function is called first when the agent transfer occurred. It then switched the active agent to the refund agent. Because I didn't implement any business logic in the trigger function, no context is provided to the refund agent. Here, I will just type, please issue me a refund for the book return. The refund status tool function is then called to complete the request. Now, if I have any follow-up requests like, what is my balance due? It will transfer us to the balance due agent, and we can inquire the balance due. For the next lesson, I will show you how to implement Guardrail, which is used to validate user input and agent output. In this lesson, we are going to learn how to use Guardrails to validate user input and agent output. Guardrails in the Agents SDK are mechanisms that run in parallel with agents to validate user input and agent outputs. They help ensure the integrity and appropriateness of interactions by screening inputs for relevance or blocking undesired behaviors. There are two main types of guardrails: input guardrails and output guardrails. Input guardrails check the user's initial input before the agent processes it, versus output guardrails validate the agent's final response before delivering it to the user. Let's look at an example. How to implement input guardrails. To implement agent guardrail, import the Python dependencies and set up the LLM model shown on the screen. Guardrail function output is a data class used to represent the result of a guardrail function. Input guardrail tripwire triggered is an exception that gets raised when an input guardrail detects a violation. It checks the initial user input before processing. An input guardrail is a decorator used to define input guardrails. To implement an agent guardrail, first, we need to define a data model for the guardrail output for the validation. One of the requirements is the data model must contain a field that is a Boolean data type to specify if the guardrail condition is triggered. In this case, the isPython question field is used as the trigger condition. Reasoning field is optional, but it will provide better context to help the agent to explain why a request is rejected. Next, we need to create a guardrail agent that is responsible for analyzing input to determine whether if user's request violates a predefined rule. And in the output type parameter, assign the guardrail data model as the data type. Alright, to validate user input, create a guardrail function with run context wrapper, agent, and user input as required parameters. The CTX argument provides local execution context, which contains contextual information to provide additional data for validation. Agent should be self-explanatory, which represents the agent that triggered the guardrail function. And input is the actual user input that needs to be checked for violation. Inside the function, use the guardrail agent to validate the input and return the output as a guardrail function output object with output info as the guardrail data object we defined before. And the tripwire trigger field will immediately stop further execution if the condition is set to true. To use the guardrail setup, here I will create a function tool to simulate a tool call. In the agent setup, in the input guardrails parameter, insert the guardrail function that validates the input. Noticing that for the input guardrails parameter, it accepts a list, which means you can attach multiple guardrail functions to a single agent. When multiple guardrail functions are attached to an agent, each guardrail function will run in parallel when the agent receives user input. If any one of the guardrails triggers its tripwire, the execution is stopped immediately, and an input guardrail tripwire triggered exception is raised. If none of the guardrails trip, the input proceeds normally to the agent. Here, let's insert the main routine to test it out. If we look at the input here, we are instructing the main agent to make a tool call first, then tell us how to write a hello world program in Python. Based on the input, the guardrail agent is most likely going to set the is Python question condition to true, which will raise the output guardrail tripwire trigger exception. Now let's run the script to see what happens. If we look at the log, the function tool is called because agent is running both tasks in parallel, and the user input is passed to the guardrail function for validation. And from the guardrail result, the is Python question field is set to true by the guardrail agent. Therefore, the exception is raised and the execution stops. The output guardrail works very similar. Instead of using input guardrail specific class and decorator, they will become output specific. And this time for the output response, I'll add an extra layer by converting it as a data object called message output. The guardrail data object and the guardrail agent, they still work the same. And instead using input guardrail decorator, we will apply the output guardrail decorator to the guardrail function. Finally, in the main agent setup, assign the guardrail function to the output guardrails parameter. And that's all the differences between using input guardrails versus output guardrails. Now let's run the script. If we look at the log here from the output response, here the input label should be output. But if we look at the executions, both the output and tool call are generated and called. The output is then passed to the guardrail function for validation. Again, we know the input is a Python-related question. Therefore, the guardrail exception is raised. And that's everything you need to know to implement agent guardrails. For the next lesson, which is the last lesson, we will learn how to work with event hooks. In this lesson, we are going to learn about hooks. Hooks in the Agents SDK framework refer to the lifecycle events that allow you to observe and interact with an agent's execution at different stages. These hooks can be useful for logging, prefetching data, modifying behavior dynamically, or handling errors. There are two types of hooks, run hooks and agent hooks. Both serve very similar purposes, but operate at different levels in the Agents SDK lifecycle. Run hooks are tied to a full agent run and can involve multiple agents. Run hooks are usually used in workflows, logging run level operations, and the modified run configuration. Agent hooks, on the other hand, are tied to a specific event and are usually used to log agent activity, modify inputs, or handle errors at the agent level. The usage of agents hooks and run hooks is very similar. With agent hooks, you assign the hook object at the agent level, and with run hooks, you assign the object at the run level. For the example, I will only share how to use the run hooks lifecycle. In the script, import the Python dependencies. The run hooks class allows you to observe and interact with the entire execution lifecycle of an agent run. To connect an agent run with the hooks, create a class with run hooks as the base class. Inside the class, create the methods associated to the hook events. Each method is called based on the lifecycle event occurred, and in each method, insert the business logic you want to implement, and that's it. And you can create multiple hooks class to handle multiple scenarios. To use the hooks class, create a hook object. Then set up the function tools and agents. In the main routine, when you initialize the agent run, in the hooks parameter, assign the hooks object we just created. Now, if we run the script, based on the event lifecycle, from the log, we can see when each event method is called. And that concludes this OpenAI Agents crash course. I hope you find the video useful. If there are any tutorial ideas you have in mind and you would like me to cover, please leave them in the comments below. Also, if you are a Patreon member, you can download the source code from the link in the description below. And don't forget to like the video and subscribe. Happy coding. See you in the next one.